In this video, we're going to be looking at several techniques for coming up with Taylor series for a function if that function is not simple or straightforward. Your course pack talks about various techniques: substitution, addition and subtraction, multiplication, and differentiation and integration. I'm going to do one video on substitution. That's this video. Then within this video, I'll talk briefly about addition and subtraction. Basically, all that involves is if you want to find the Taylor series for a function that contains two terms, the sum of two functions or the sum of two expressions, then you simply need to find the Taylor series for each of the two expressions, each of the two functions, each of the two terms, and add those Taylor series together. Once you've got the sum of two Taylor series, that's equal to the Taylor series of the sum of the two expressions inside the Taylor series. So that's pretty much all there is for addition and subtraction, although I'll touch briefly on it as I do the rest of this video. Then I'll do a separate video for multiplication. That'll probably be a pretty short one, and another one for differentiation and integration. So to start with, I want to talk about how to find the Taylor series expansion for a function we've worked with before, but one that's, instead of being based at 0, it's based at 2. In this problem, we're asked to find the Taylor series expansion for f of x equals e to the x based at 2. Well, we know the Taylor series expansion for e to the x, and in fact, we know that that's one of those functions that actually equals its Taylor series. We have e to the x is equal to I goes from 0 to infinity, and it's x to the I over I factorial. Well, remember that the formation of a Taylor series comes from the Taylor expansion, the Taylor polynomial. And actually, I'm going to put this down here. We had the function evaluated at b plus the first derivative of the function evaluated at b times x minus b plus the second derivative of the function, no, see, I did it again, plus 1 over 2 squared f double prime at b times x minus b squared. I said squared down here too, didn't I? Say 1 over 2 factorial. Sorry about that. Plus 1 over 3 factorial f triple prime evaluated at b times x minus b cubed, and so on up to the nth, 1 over n factorial times the nth derivative evaluated at b times x minus b to the nth power. With the e to the x function, each one of my derivatives is going to be e to the x. Where am I here? E to the x. And then I'll have x minus b, but when it's centered at 0, b is 0, that's just x. So that's going to be x. This is going to be x squared, x cubed, x to the nth power. And then, of course, I have this 1 over something factorial in front. And you can see, and of course, these are all added together. You can see in this thing, this 1 over n factorial, right? That becomes this over I factorial here. And then I have x squared, x to the third, so I get that x to the nth. That's what becomes the x to the I. And then I have e to the x, e to the x, e to the x. But I'm evaluating this at b. This is f of b and f prime of b. Well, if this is b, e to the b is e to the 0, right? So that's going to be a 0, as will each of these. Well, e to the 0 is 1. So we end up with an e to the 1, or sorry, an e to the 0, or a 1 in each one of these terms. And so if I factor that 1 out, factor out the e to the 0, that's just equal to 1, I'm left with 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus, and so on, up to x to the n over n factorial. This is just 1, and if I rewrite this as a sum, I get this. So this works for e to the x, but only if b is 0, only if it's centered at 0. This is actually a Maclaurin series. We want to do the same thing, but we want it for the function based at 2. So that changes several things. First of all, it changes that e is not raised to the power of 0, but to the power of 2. These are going to be 2's. And it also changes the fact that these are not just x's anymore. They're x minus 2's. This one would be x minus 2 quantity squared. And this is also x minus 2, and this is also x minus 2, right? So there's another change there, and that changes this thing as well. So one way to handle this would be to rewrite it as I've just done here, factor out the e squared, write the x minus 2 squared, x minus 2 cubed, x minus 2 to the nth power instead up here, x minus 2 to the ith power, and then have over n factorial. So that would be one way to do that. But some of the functions that we'll be working with aren't that straightforward. So it would be useful to have a way to attack a problem like this without having to work it all out explicitly like this every time. Based on the fact that we know what the Taylor expansion is for the Taylor series is for e to the x when it's based at 0, let's see if we can find a way to substitute in for x so that it shifts the whole thing to the right, essentially, and to the value b equals 0, makes it centered or based at b equals 2. Sorry, I said 0 again there, I meant 2. We'll center it at 2 and see what we can get. My proposal is, based on this down here, my proposal is that e to the x at 2, I'm not sure how to annotate that, I'll say based b equals 2, would be e squared. If I factor out an e squared, my nth term would look something like this. E squared times x minus 2 to the power of I over I factorial. And I'll sum those, I'll add those all up. And I'll go from I equals 0 to infinity. So that's what I propose based on my ham-fisted brute force attempt to figure out what it is when it's based at 2. But now let's see if we can do it using a simpler method. Okay, one thing I've done here is put a big fat question mark here because I've brute forced my way through this, and I'm proposing that the answer I'm going to come up with is this answer here, but I want to do it a different way. So in this case, because we're working with the substitution, idea of substitution for the first time, I've kind of written out the answer, but I've highlighted the fact that we want to find it a different way. So this is a little bit like doing an exercise in a textbook where you look up the answer in the back of the book. The answer's there, you just have to try to match your work and your answer to the answer in the back of the book. In the real world, of course, you don't always have the answer. You need to figure out what it is. So one of the things we can do is substitution. And substitution is, in a lot of ways, it's a lot like doing substitution in integral calculus. If I were in an algebra class, I would say, I want to shift this thing 2 units to the right. So let's substitute in something I'm going to call u substitution. I'm going to call it u. I'm going to substitute it for x minus 2 because right now this thing is centered at 0, but I want it to be centered 2 units to the right of 0. So I'm thinking about it as my work is being shifted 2 units to the right. If I make that substitution, then I can now think of e to the x as e to the u plus 2, right? If I add 2 to both sides of this equation, I get u plus 2 equals x. So e to the x can be thought of as, I wrote 1 there. Why did I write 1? E to the u plus 2. There we go. That's e to the u times e to the 2, or e to the 2 times e to the u. Now, e to the 2 is just a constant, but e to the u can be written as, because we know that has its it's equal to its Taylor series. E to the x can be written like this. E to the u can be written like this. I goes from 0 to infinity, u to the power of I over I factorial. But what is u? Well, it's just x minus 2. So I can write this as I goes from 0 to infinity, x minus 2 to the power of I all over I factorial. And this is exactly what we have up here. Down here, my e to the 2 is outside the sum, but based on the properties of summations, right, I can put that in there. So this is equal to the sum, as I goes from 0 to infinity, of e squared times x minus 2 to the power of I all over I factorial. Now this was a pretty simple, straightforward example, but the idea is to illustrate how substitution works. Let's try one that's not quite so straightforward. Okay, in this problem, we want to find the Taylor series expansion for the function f of x equals 1 over the quantity 2x minus 5. Right now, the only Taylor expansion that we know, the only Taylor series we know that looks anything like this is one that looks like this. We know that this function, 1 over 1 minus x, is equal to its Taylor series where I goes from 0 to infinity for x to the power of I. But this thing doesn't look like this function. The question is there something we can do to this function to make it look like this function? And the answer is yes. It's of similar form. So let's see if we can manipulate this so that it looks more like this. The first thing I want to notice is that the x term in the denominator of my given function comes first, but in the known function, the function whose Taylor series I know, it comes last. So the first thing I'm going to do is rewrite 1 over 2x minus 5 as 1 over negative 5 minus 2x. And the next thing to notice is that I have a 1 here and I have a 5 in this function. So let's divide by 5 just in the denominator. I'm going to have 1 over negative 5 times 1 minus 2/5 x. I should probably move that 1 over just a little bit. Now, I can write this as negative 1/5 times 1 over 1 minus 2/5 x. And at least this part of it is starting to look a lot more like this right here. The only thing that's wrong with it is I have a multiplier, a constant in front of my x. So why don't we let u equal 2/5 x? Because then I can write this as negative 1 over 5 times 1 over 1 minus u. Now in this form here, remember that if I'm going to rewrite this using in its form as a Taylor series, I have to remember that u must be between negative 1 and 1. Well, u is 2/5 x. So for 2/5 x to be between negative 1 and 1, x must be between negative 5/2 and 5/2. So I have this restriction on my given function, this function here. Let's move this. Oh, I can't. I can't move just that piece. So I'll rewrite it instead. X is between negative 5/2 and positive 5/2. And now I can write my expansion. This is going to be equal to negative 1/5 times this thing right here. Well, this thing we know is equal to its Taylor series, except I'm using u instead of x. So I'll have the sum, I going from 0 to infinity, of u to the power of I. But I know what u is. I have a way to write u. I goes from 0 to infinity. U is just 2/5 x. So there is my expansion. Now we like these things in a lot of cases to be complete sums. So I kind of like this -1/5 to be inside here. So I'm going to rewrite it again. I have the sum, I going from 0 to infinity, of -1/5 times, and now I'm going to sort of write this expression here slightly differently. I'm going to write it as 2 to the I over 5 to the I times x to the I. And then noticing that I have the same thing in the denominator twice here, I can write this as, I don't like that infinity. I can make a better one. I'm going to have 2 to the I times x to the I, or 2x to the I, over 5 times 5 to the I, or 5 to the I plus 1. And then, of course, I have this negative in front here. Depending on the context in which you're using this, you might want your x to be isolated. So I'll write this one more time, and this is what your course pack has, the form your course pack is using. I'm having trouble with my infinity again. There we go. The only difference I'm going to make now is I'm going to leave this x to the I kind of by itself. So I just have -2 over 2 to the I, or 5 to the I plus 1 times x to the I. Your course pack has this in parentheses. So that should now match, let's see. Yes, that now matches what your course pack has. Your course pack uses K as its index also. I should have said that a long time ago. I've been using I just because that's what I learned. That's how I learned how to write these. My index has always been I. But I think the course pack makes a good point. I don't know why they've chosen K, but I think you can probably see as I've written some of these. Let me just write this out again using K. As I've written some of these, you can see that I is actually often quite difficult to kind of squeeze in there with the dot you have to put over it. I know it's kind of a silly thing, but when you're actually writing these sort of by hand, now that one's not too bad. But down here, I've got 5 to the I plus 1, and K plus 1 is just kind of easier to see. It's easier to write. It's easier to sort of figure out how to squeeze that in, make space for it. It doesn't really matter. I have a preference for I, but K is equally as good, it's just as good. Some people use J, and some people use Greek letters, like you might see an alpha or some other Greek letter. All of that's really kind of immaterial. The point is, this is one of the ways that you can use existing known Taylor series to determine what a Taylor series is for some other function, slightly similar function. And this one wasn't as obvious, but what I did here was I took something that I vaguely recognized the form as being like this one here, and then I just manipulated it algebraically until I could make it in that form. I also have to take my restrictions along with me. Now my restrictions in this case, if I rewrite this, -5/2 to 5/2, this is my radius of convergence, or my interval of convergence for this, not for this function, sorry, for the Taylor series, for the function. This is my radius of convergence. There's one other thing I'd like to point out here. Your course pack kind of just blows over it very, very quickly because it's a really fairly minor point. We already know this, but I want to remind you of it, and I want to kind of highlight it just for a moment. One form I have this thing written in at the moment is this. And I'm not sure that's the best version of this, but it'll do for now. And here's another one. I said these two things were equal to each other, and I think it was just because I could move the 1/5 in, the negative 1/5. And that's due to a property of sums, right? We said back in calculus, I think it was calculus 1, it might have been calculus 2, that you could either leave this constant inside here, or you could draw it out. You could pull it out, put it out in front like it is here. Either way, that what you're doing here is multiplying this sum by a constant. So if you add these all up and then multiply by negative 1/5, you'll get the same thing as if you add these all up and multiply each one by negative 1/5, or multiply each term by negative 1/5 and then add them all up, right? You're effectively factoring out a negative 1/5 if you write it this way. So multiplication by a scalar or multiplication by a constant is allowed, and it's allowed in Taylor series because it's allowed in summations. Now this has been example 5.3. Example 5.4 is similar. It's a little bit more convoluted. We have 1 over x squared plus 4 instead of 1 over 2x minus 5. But I think your course pack does an adequate job of explaining it, and the pattern of the process is very similar to the one we've just done. The one observation I would make out here is that it's not necessarily obvious that one of the substitutions you have to make is the introduction of a negative. So when you do the substitution, you have 1 over 4 times the quantity 1 plus something, and you want that 1 plus u, except you don't want 1 plus u. You want it to be 1 minus u. So the thing you substitute u in for, you have to include the negative in that. So kind of keep an eye out for that. Other than that, this example is pretty much like the one we've just done. Okay, in this problem, we're looking at a function that is a ratio of polynomials. It's a rational function. And we're asked to find a Taylor series for it based at b equals negative 1. So the first thing I want to do is recognize that wherever I might have in my Taylor polynomial an x minus b, I want that to be x minus negative 1, which is x plus 1. So instead of x minus b, I have x plus 1, and I'm going to let that be equal to my u. This is essentially what we did with the first example we looked at. There we had b equals 2, so we said let u equal x minus b, which meant that u equaled x minus 2. And here what we're saying is that u equals x minus b, which is x minus negative 1. So that's my substitution in this case. Now that I have that, now that I've made that decision, I've got x squared plus 3x plus 5 over, let's try that again, over, that's much better, x minus 2 times x squared plus 2x plus 5. I thought so. I wrote that down wrong. This is supposed to be a 3. And especially since this is the problem in the course pack, I want you to be able to follow along either here or in the course pack and have the same problem. Plus, the things I need to happen wouldn't happen if I have the wrong number there. So x squared plus 2x plus 5 in the denominator. Let me just double check that I have that all right now. It looks pretty good. And now I'm going to make that substitution in line. Everywhere I have an x, I need to do this. I have x equals u minus 1. Everywhere I have an x, I'm going to write a u minus 1. So I have x squared plus 3 times u minus 1 plus 3 all over u minus 1 minus 2 times u minus 1 squared plus 2 times u minus 1 plus 5. And when I simplify that, I get u squared minus 2u plus 1 plus 3u minus 3 plus 3. And down here I'm going to have u minus 3 times u squared minus 2 plus 1 plus 2u minus 2 plus 5. Got a little carried away with my division bar there. And that is equal to u squared plus u plus 1 over, I'll just go with u minus 3 for now, and then here I have, that should have a u in it, u squared minus 2u plus u2, those are gone. Plus 1 plus 5 is 6. 6 minus 2 is plus 4. Now, I hope that you remember from calculus, where did we do that? Calculus 2, integral calculus. You can write this as two separate fractions by observing that this is a linear factor and this is an irreducible quadratic factor. And so I can write this as a over u minus 3 plus bx plus c over u squared plus 4. And of course, this also needs to be a u, just because that's the variable I'm working with here. And then I need to use partial fractions to figure out what a, b, and c are. Now, should I take the time to review that here? I'll show you how I do it. It's not how everybody does it, but my claim is that these two sides are equal. This sum of two fractions is equal to this. And what that means is that the right-hand side, in order to have a common denominator, needs to be written as a times u squared plus 4 plus bu plus c times u minus 3. And that's then going to be over the common denominator u minus 3 times u squared plus 4. But if that's equal to u squared plus u plus 1 over the same denominator, then it must be true, put this up here, that u squared plus u plus 1 is equal to the numerators. The denominators are equal now, right? So the numerators must also be equal. So this numerator must be equal to this numerator, and that numerator is, if I simplify it, if I expand it and simplify, I get a times u squared plus bu plus cu plus my constants 4a. Oh, I have a bu squared as well. So this term is not quite correct. Let me start over. I have au squared here, and I have a bu times a u there. So I have a u squared plus bu squared. If I factor the u squared out, I get that. And then my linear terms are, see, bu times negative 3. So I have negative 3 bu. Looks like that's it, actually. Oh, and then plus cu. So I have negative 3b plus c times u. And then I have, for constants, 4a and minus 3c. So 4a minus 3c. This is not the only way to do this, but this is how I learned how to do it, so it's my preference. Now, the observation we can make now is that terms with the same power must be equal. So the coefficients must be equal, and that means that a plus b equals 1. Get rid of a little bit of this line here. The u's must be equal, so their coefficients, those terms must be equal, which means their terms must be equal. Their coefficients must be equal. And so negative 3b plus c also equals 1. And lastly, this constant has to equal this constant. So it must also be true that a, where am I? 4a minus 3c also equals 1. And this is a system of equations. And solving that system of equations will give me values for a, b, and c. And I'm not going to take the time to do that on screen because this is not a class in solving linear or solving systems of equations. What I will do is I'll go off screen and figure it out and come back and tell you what those three values are. All right, it turns out that A is 1, B is 0, and C is 1. So that means that I can rewrite this, wrong pen, I can rewrite this sum of two fractions as A, which I now know to be 1, over u minus 3, plus B is 0, so my BU term is just gone, plus C, which is 1, over u squared plus 4. This expression here, once it's simplified to this expression here, can be written as this expression here. So I'm going to use this one now because I already know how to change this fraction into something I recognize and can find, let's see, u. First of all, I want negative 3 minus u. And then I'll factor the 3 out. So I have 1 over negative 3 times 1 minus u over 3. And then I'll substitute something like maybe j or t for u minus 3. And I'll have a negative 1/3 times 1 over 1 minus t. And I know the sum, I know the Taylor series for this expression, for this function, in terms of t. Once I've figured it out, I'll have to back substitute u over 3 in it. And once I figure that out, I'll have to back substitute x plus 1 in. But that process is fairly straightforward because we already know how to do this problem, right? We know how to find the Taylor series for this. Same thing with this one. This was the one I skipped over, example 5.4. I said, you know, your text or your course pack does a very good job of explaining this. One thing you had to watch out for was the introduction of a negative sign. So if you haven't followed that one, go back and look at example 5.4 and you'll see how to do this substitution. Now, one thing I sort of skipped over is that the sum, let me erase some of this stuff down here. The sum of two sums, I'll write it this way. If I have the sum of one function and the sum of another function, then I can write that as the sum of the sums of the functions, and vice versa. So I don't like that sum. Let's see if I can fix it. That sigma. Okay, that'll do. So what I have, where am I? What I have here is sort of this, right? This form. I'm trying to find the sigma notation for this combination, this sum of two expressions. Well, I can do that. I can find this by just finding the sum of each term, as it were, by itself. So instead of finding the sum of this function plus this function, I'll find the sum of this function and add it to the sum, not the sum of this function, but the Taylor series for this function, and add it to the sum, the Taylor series for this function. In order to do that, I'm going to need a little more room, so I'm going to erase a few things here. I'm going to get rid of this little note that I made, and let's see, what else can I do? There's really not a lot, actually. I could move this, but I'm sort of running out of room. Let's do, each of these was equal to the one before, and then let's do this, that I went up here, and then let's put this here, and I'll just put a dotted line to help us remember that that wasn't from immediately the line above, but from down here. Okay, so that's equal to that. And what I've been doing here is changing this expression, changing this function into a different form. So now I've got it in this form here, keeping in mind that I've changed my variable from x to u by the virtue of this, let's see, where am I? Where's the substitution that I made? Ah, here it is up here. I made this substitution in the first step, I simplified that. I used partial fractions, and I've got it in this form here. So now this thing is in the form of two much simpler functions than the expression that we were given. And we worked on an example very much like this one, so I know how to find the series for this one. I can't just replace it with its series yet. There's a little bit of work I need to do. And we didn't do it together, but example 5.2, I think it was example 5.4, we learned how to do this series. So this one I can actually just replace with the result of that work that we did earlier, or didn't do, as the case may be. The sum as I goes from 0 to infinity of negative 1 to the power of I times u to the power of 2I over 4 to the power of I plus 1. And for this one, we need to do a little more work first. We need to rewrite this. It's not in the form 1 minus u. It's in the form u minus a constant. So let's rewrite this as 1 over negative 3 minus u, and then rewrite it again as 1 over, and let's pull out that 3, factor out that 3. That gives me 1 minus u over 3, and that's still plus this other sum. And then we can replace the u over 3. We can do another substitution. Let's let t equal u over 3. And that gives me negative 1/3 times 1 over 1 minus t plus this sum. Now, I'm out of room again. So at this point, I'm going to erase some of my screen, I think. I'll erase from here down, just on this side. And I'll erase my the work that I did finding the coefficients when I did my partial fractions work. So I'm going to erase not this line here, but everything kind of below and to the right of it. And what that means is that we now have this equation here, or this expression rather, is equal to this expression, having used this substitution. Actually, the substitution we used was this one here, but they're equivalent. So having used that substitution, we have this expression is equal to this expression, which is in turn, after having done some work here, equal to this expression. So if I move some things around, then I can continue what I was working on before. Now I have that this is equal to negative 1/3 times the sum for this expression here, which we know from example, it turns out that that was example 5.3. That's going to be the sum as I goes from 0 to infinity. Now, when I had it as a 1 minus u, or 1 over 1 minus x, the sum was the sum of x to the power of I. When it was a u, it was u to the power of I. This is a t, so I have t to the power of I. That's the variable that I'm working with, right? Because I substituted t in for something, and then I substituted the u came from another substitution. So, but right now I'm working with t, and I have to use t here because that's the form that I can replace this sum with. It has to be in that form. And when it's in that form, it's got the variable t in it, right? So that has to be a t here. But t, if you'll recall, I'll come back to the second part here in just a minute. T is just u over 3. I'm having trouble writing my infinity to my liking. So if I have u over 3 in place of t, I get that. And then, and of course, I'm going to have to come back and put the second sum in here. I'm not done with that. I'm just trying to focus on the algebra for this sum here at the moment. U also is a replacement. So let me back substitute for my u. I get, let's see, u is x plus 1, so I have x plus 1 all over 3 to the power of I. I'm going to split that up now and write it that way. And then I'm going to remind us that because this is a constant, I can either pull it out or bring it back in. So I'm going to bring it back in. My second term will go there. So I'll have the sum, I going from 0 to infinity, of negative 1 over 3 times. So the numerator is 1 times x plus 1 to the power of I. And the denominator, as in the previous example, as in example 5.3, the denominator is going to be 3 to the power of 1 times 3 to the power of I. So I'll have 3 to the power of I plus 1. And that is the expression in its sort of final summative form for this first term here. This first term here simplifies to this. And then to that, I'm going to add the second sum. And I already have that. It's the form I goes from 0 to infinity of negative 1 to the power of I. Let me see if I can scoot this over a little bit. Okay, that's better. So I had negative 1 to the power of I times u, but u is x plus 1, so I'll write it as x plus 1, to the power of 2I all over 4 to the power of I plus 1. Now, there's a potential here for some confusion. I've got I as my dummy index in this sum and in this sum, so I'm going to change one of them. And the primary reason for that is just to avoid confusion. So I'll get rid of that I, and this one, and of course this one here. And I'll replace those with, let's see, which letter should I use? I think I'll use K. My inclination is to use I and J, but I do think K is easier to see, so I'm gonna use K in this one. And that is how you would write this this expression as a sum. Well, it's not a sum, it's two sums, isn't it? But that's how we would have to approach one of these. As in Calculus 2, whenever I see a rational function like this, I think, partial fractions. And so partial fractions is the trick we had to use here, and that got us to a place where this expression could be written this way. In particular, well, let me go back up here. It can be written this way, and we know how to approach this one. We can write that as a sum. Just follow down here. And we also learned the result of this exact expression in a previous example. So we just copied that example down. We made a few adjustments, and this is my result, right? Because I had to split this up and write it as two fractions, I have two sums. Now, arguably, one of the things we like to be able to do is to sort of generalize as much as possible. And so another way to write this would be as a single sum with sort of some, I don't want to call them restrictions, but maybe specifications. A single sum with specifications about how the index is to be used. So I'm going to do that on the next screen. Well, no, I'll do it on this screen, but I'm going to have to erase a few things typically in order to make room for myself. So I'm going to leave this line here. I'm going to leave this line here, and maybe I'll leave this line as well, and I'll say that that is equal to this line here. So I'm going to move this up to here and then replace this line and erase everything else. Okay, now that everything is in its new place, let's take a quick look at the situation and make an observation. The only thing that this sum and this sum have in common is that there's a factor of x plus 1 in both of them. Now, your course pack continues to write this until this step continues to write this as x minus negative 1, but ultimately that becomes x plus 1. The problem is that this sum here uses every factor, x plus 1 to the 0, x plus 1 to the 1, x plus 1 to the 2, whereas this term, this sum, only uses every other one. every other factor. So, for example, when k is 0, I get x plus 1 to the 0. But when k is 1, I get x plus 1 to the 2. Here, when I is 1, I get x plus 1 to the 1. I'm going to get x plus 1 to the 2, and then x plus 1 to the 4, and then x plus 1 to the 6. So it's skipping every other factor. So one way that I could consider writing this is as the sum of some function times x plus 1 to some power, we'll just call it n, and I'm making that my index. So I have a sub n here and I have an n here. So I'm going to say that n goes from 0 to infinity. And we're going to say that this is my answer depending on what a sub n is. And a sub n is either going to be this thing right here, right, for every single, without the x plus 1 in it, because I have x plus 1 here now. It's either going to be negative 1 over 3 to the power of 1 plus x. Let me just write that in. Negative 1 over 3 to the power of, I said 1 plus x, I plus 1 there. And that's going to be true. That's going to be my my a sub n. My a sub n is going to include this for every single power of I, right? For every other power of I get this one and this one. So I'm going to have negative 1 over 3 to the I plus 1 plus negative 1 to the power of k, because that's the dummy variable we were using in that situation, in that sum. And I already have my x plus 1, so I don't need that. I'm going to have 1 over, then, what's left of that one? 4 to the power of k plus 1. Let's rewrite this up here so that it's not quite so tight. Okay, so now I have this situation when n is an even number and this situation when n is an odd number. But the problem is I don't have these written in terms of n at all. I have them written in terms of I and k. So let's figure out how we can write. And the other thing I want to do is point out that what these two things are, this line here and this line here, is those represent a sub n, right? This is the function that's going to go in this position when n is an odd number. And this thing here will go in that position when n is an even number. I'm going to try moving this up a little bit. There we go. So that I can write down here when n is an even number. And so what we're saying here is that this thing is sort of defined by whatever a sub n is. And a sub n is equal to one of these two things. It's equal to this when n is odd, and it's equal to this when n is even. Now, let's see if we can figure out how to make bring the n into play. I think it's pretty obvious that when n is an odd number, this is just going to be n. And I can kind of test that. Let me use yellow. Use a yellow pen there. So I have an n and an n, because for that term, when n is odd, I have 3 to the power of 0 plus 1. When n is even, I have 1 plus 1 here, and then 2 plus 1. Sorry, 0 plus 1. Nope, other way around. 0 plus 1, 1 plus 1, 2 plus 1, 3 plus 1, and so on. 4 plus 1. When n is odd, we use this. When n is even, we use this. So that part of it is okay, but now we have to figure out how to write this part. We've already got the x plus 1 to the n. That part right there is taken care of. So when n is an odd number, this will be x plus 1 to the power of the odd number, 1 or 3 or 5. When n is even, it'll be x plus 1 to the power of 2 or 4 or 6. But that's only for this x plus 1 to the power of n piece. We still need to figure out how to write these so that they represent what pops out of this sum when n is odd. It turns out to be just this, or when n is even, it's this term plus this term. So when n is odd, we just get this. When n is even, we just get this, or we don't get just this, we get the two terms together. But I need to figure out how to write the index here as for every instance, right? If n is the even number, what is k? Well, we've already taken care of the case where n is an odd number. When n is an even number, we want all the instances of this thing to pop out. So when n is an even number, we want the index to be, I'll do that in yellow as well, n over 2, half of that even number. And the reason for that is that the number n is even, but we want every instance of this for that even number. So let me see if I can just run through one or two examples of what happens when you plug in different values for n here. When n is 1, n is odd, so you use this line, and you get 3 to the power of 2. When n is even, you run through this line, so you get 3 to the power of 3 down here. But also, if n is 2, then we have this negative 1 to the power of 2 over 2 is 1. So that's going to be an odd power. Ultimately, it's an odd power that making this a negative. And n over 2 here is going to be 1, so you get 4 to the power of 1 plus 1 is 2. The next even number after 2 is 4. So here we're going to get 3 to the 4 plus 1, 3 to the 5. But here we're going to get 4 divided by 2 is 2, and 4 divided by 2 is 2. So you get negative 1 to the power of 2, and that makes this term positive. Down here you get 4 to the power of 2 plus 1 is 3. The previous one was 2 over 2, which was 1. 1 plus 1 is 2. This one was 4 divided by 2 is 2. 2 plus 1 is 3. So you got a power of 2, and then you had a power of 3. So you're getting every power of 4, but only when n is an even number. When n is an odd number, you don't get that term at all. So I don't know that this is necessarily something we need to spend a whole lot more time on, but it's in your course pack, and it's not at all clear, I think. The author of the course pack did not make it at all clear how they got from this step to this step. So I hope this explanation helps that a little bit. Now, the other thing we were asked to do here was to give an interval where this converges. Where what converges? Where the series converges. So we need to find an interval where the series converges based on the fact that it can be different things depending on whether the index is even or odd. So what I'm going to do now is go to another screen, same video, but I'll go to another screen, and I'm going to copy down the series that we found. This series, I'll probably copy down both of these versions of our series, and then we'll take a look at how to find the interval of convergence. Okay, so here's my original expression, and here are the two versions of the series that I found for it. Down here, I've written the formula, if you will, for the series for the function 1 over 1 minus x. And recall that that has to be between the domain here, the interval of convergence here is x has to be between negative 1 and 1. When we did example 5.3, we were working with not 1 over 1 minus x, but 1 over 2x minus 5. We changed that to 1 over 1 minus 2/5 x, and then we had times a negative 1 over 5 out front. And so this was the thing, we substituted u in for that, but that was the thing in the position of x, right? So it was that thing, 2/5 x, that had to be between negative 1 and 1. And when we solved for x here, we got that x was between negative 5/2 and 5/2. And the same thing is going to apply to our situation in this example. Here we were working with, I'll write it the same way. I had a negative 1/3 out front. That's supposed to be negative. And then I had 1 over 1 minus u over 3. 1 minus u over 3. And this is the thing in that position, right? My x is in this position here and in this position here. So it's this thing, u over 3, that needs to be between -1 and 1, which means u has to be between -3 and 3. Since u was x plus 1, we now have this, which means is subtracting 1 from both sides. We get -4 is less than x is less than 2. So x has to be between -4 and 2. But then that is only for the part of the series, the first part of the series, this first term here, right? So I also need to figure out what the restrictions are, what the interval of convergence is for this term. We learned in example 5.4, remember we didn't do that one together, but it is in your course pack. In that example, we learned that the variable had to be between the values of -2 and 2, but the variable in that case was x, and the variable we were working with in order to find this series, we had to substitute a u in for, well, it was u, I think it was u minus 1, u plus 1, u minus 1 in for x. So we found our series based on u, not on x. So if we have u is between -2 and 2, then x plus 1 is between -2 and 2. And subtracting 1 from all three of these, I get -3 is less than x is less than 1. So this interval of convergence applies to the first term in the series, and this one applies to the second term in the series. And if we look at these together on a number line, I have to go down as far as -4. There's -3, -2, -1, 0, 1, and 2. This interval of convergence is between -4 and 2. -4 and 2, so it's pretty much that whole thing. And the other term's interval of convergence is between -3 and 1. So it goes from there, wrong pen, -3 up to 1. So since we need the same interval of convergence for this single sum that we've written, this is a single expression as a sum in terms of a sum, the interval of convergence has to apply to both terms. The interval of convergence, the restrictions that we have to place on the overall sum have to restrict both terms as much as possible. In other words, if the overall restriction, if the smallest interval of convergence is -3 to 1, then that is the interval of convergence for the entire series. So our interval of convergence here is -3 to 1, or as your course pet puts it, -3 to 1. And you can write that either way. I don't have any particular preference. I've always preferred interval notation myself. It just seems more compact. You can get quite specific with it using brackets instead of parentheses. But this is equivalent, and it's absolutely fine. If you have a preference for inequality notation, that's fine with me, as long as it's correct, right? By way of example, if, and this is an if, it has nothing to do with this problem, but just kind of a side note, if one of the terms here if one of the terms here had an interval of convergence from -3 to 1, and another had an interval of convergence from, I'll use a different color, from 1 to 3, for example. I'll go over this one again. Oh, you can't see them both. That's very disturbing. Then the overall interval of convergence, the smallest area covered by both of these is just this region right here, from -2 to 1, and that would be my interval of convergence in that case. Now that's nothing to do with this problem. I just stuck it in there to sort of show another example of how you would take two intervals and combine them and overlap them. It's the overlapping area that we're allowed to use. That's our interval of convergence for the overall problem. This idea is actually from elementary algebra, but it's maybe been a while since we actually talked about it. So, well, I'm going to erase that from this final screen because that is all I'm going to do on this video. And this screen now it represents the work that we did to find the Taylor series for this function based at b equals -1. And on this screen in particular, its interval of convergence. So this video, it's been a pretty long one. This one has been about substitution, and I've extended that into this last example for finding the Taylor series for this expression here. And I did have to use substitution here. I had to rewrite this expression using partial fractions and then find a way to write the two individual terms. But this video also therefore addresses the idea of addition. The technique for finding a Taylor series using addition is, as I mentioned at the very beginning of this video, that if you want to find the Taylor series for the sum of two expressions, I'm just making one up now, then all you need to do, in theory, is find the Taylor series for this expression, find the Taylor series for this expression, and add those two Taylor series together. And that's what we have here. And then depending on the situation, you may be able to combine them easily, or in this case, it was a bit more convoluted. To combine them into a single series, we had to introduce this thing called a sub n and define what a sub n had to be based on whether n was even or odd. This was a very specific sort of example. But the idea for addition is that to find the Taylor series for this sum, find the sum of the two Taylor series. So we've addressed substitution in this video, and we've also addressed addition and subtraction. In the next video, we'll talk about differentiation and integration, and in the final video, we'll talk about multiplication.